Chapter or Module 15, Fire Detection and Protection Systems. Fire detection and protection systems are critical safety systems designed to rapidly detect, warn through a notification on the alarm panel, okay, on the display panel in the cockpit, and suppress fires in aircraft compartments. Because in-flight fires pose an immediate threat to aircraft integrity and occupants. These systems are designed with high reliability, redundancy, and clear crew indications, which means that they can be counted upon to warn and to suppress fires, okay? And they are redundant so that the system would be fail-safe. In case one sensor had failed, you would have multiple other sensors that can detect the same thing. This is below an illustration for different fire sensors that are mounted. Of course, one of them would be inside the engine, okay, another would be at the wings, different compartments of the aircraft. Here you would have the fire detection card that would measure the change of the resistance. Usually the detector would be the RDS, that is a resistance changing because of the temperature or the heat. This card would send the detected signal to the AMS. Okay, once actually it detects fire, it would send the warning or like the alarm back to the cockpit. Okay, you have like fire indicators for the engines, both left and right, and you have the fuel control cutoff that would be necessary in case you have a fire in one of the engines, plus an extinguisher that would extinguish the fire within the engine. That would be in flight. Also, a speaker that is connected to this card for an early warning of fire on board. So in this illustration, you have the engine fire extinguisher bottles. Okay, these are mounted to the engine. You have a controller that would be connected to the engine and APU fire panel. Okay, this button would be pressed in order to extinguish the fire by activating these two extinguishers in case of engine fire. And the warning systems all are connected also to the engine sensors, okay, and the extinguishers, all of that panel. Fire zones and detection methods. 15.1. Fire zones in aircraft. So the fire zones are areas where you would have a potential fire, okay? These are the zones where fire detection and or suppression is required due to the presence of flammable components or fluids or any type of wiring that is susceptible to heat, and like you can consider anything that can be incendiary, that can cause a fire event or that can feed into a fire. So any area of high temperature or electrical equipment, electrical wiring, electronic components, like the areas near the wings which house the fuel, definitely. All of these, okay, require the capability to detect the fires and also to suppress the fires, all the way to like extinguish fires on board. So these fire zones include engine nacelles, auxiliary power unit, APU, compartment, which starts the engine in mid-flight in case of a flameout. It can start the engine on the ground as well. Usually they started using like a power truck. Cargo compartments, also the undercarriage, because you have luggages that are susceptible to fire, lavatories or the bathroom on board, and also electrical and avionics base. Each fire zone is classified based on accessibility. What are these classes? You have Class A, which is accessible in flight, like the lavatory, for example. Class B, inaccessible but with fire detection and crew intervention. Okay, that would be like it can be intervened for via the crew, okay, and it can like the fire can be detected. And finally, Class C is inaccessible with fixed fire suppression, like the engines, for example. Okay, these are inaccessible. Fire detection methods. Thermodetection. Thermodetectors sense abnormal temperature increases. So you have overheat detectors that trigger at a preset temperature, and rate of rise detectors that trigger on rapid temperature increase. So overheat trigger at a preset temperature value, but the rate of rise detector type, it triggers on rapid temperature shift, but it would be an upshift, a sudden increase or a rapid increase in temperature. That would be the trigger. The rate of rise condition should be greater than the critical rate of rise for it to be considered as an incendiary event that should be alarming for the crew. Okay, that should trigger the alarm. So dt over d lowercase t, which is the change of temperature in respect of time, or the derivative of the temperature in respect of time, should be greater than the critical change for it to be considered alarming and trigger the notification at the cockpit. Now, the detector works like this. So you would have an RDS, which is like a thermal resistance, that would change its value. The resistive value would change based on temperature. So when you have an overheating event, the material within the resistance, which is a conductive material, would start dilating, and the molecules would start going apart from each other, which would decrease the value of the current going through it. Okay, so once this current value decreases, that would be perceived as an overheat, as a high temperature. On the other hand, like in reciprocity, when you have a cold temperature or a normal temperature that's not hot, this conductive material would be compressed against each other. Okay, so it would be recessed and it would be close to each other, allowing more conductivity and more current to flow through. That would be perceived by the system, by like the device, the card, the detection card, as acceptable low temperature. So in other words, it would be an indicator that the engine is running without overheat. Okay, and there's no fire on board. Continuous loop detection. Continuous sensing elements run through fire zones and change electrical characteristics, mainly the resistance value, when heated. Resistance variation is given by RT, so the variation of resistance in respect of the temperature, because it would be a function of temperature, is equal to R0, which is the original resistance in cold weather, okay, the original value of the resistance, multiplied by 1 plus alpha delta T. Delta T is the temperature change, multiplied by alpha, which is the resistance sensitivity to temperature variation. Okay, alpha, or the sensitivity of the RDS of the thermal resistor or thermal resistance detector, is given by 1 over R0, the original resistance value, multiplied by the derivative of the resistance in respect of temperature. Okay, or the change of resistance rate, the change rate in respect of the change of temperature, or the R divided by dt. Optical and smoke detection, which is another type, used mainly in cargo compartments and lavatories, and it uses the light scattering principles. So, the amount of scattering of light, or the percentage of scattering of light, is proportional to the number of smoke particles. Now, let's elaborate further on how the smoke detector works. You see, the smoke detector is made of, on the inside, of a light source that would be projecting its light on a photodiode. The photodiode it's like a diode that is sensitive to light. So as long as it is receiving light, it would be conducting the current, acting as a closed circuit, okay? A closed switch. Now, when smoke goes between the light source, so during a smoke event, when the smoke goes between this lamp and the photo sensor, the photodiode, what will happen is a blockage of light, even if it is a partial blockage depending on the sensitivity. This blockage of light, when the smoke prevents that light from getting to the photodiode, would cause the photodiode to actually switch off, meaning it becomes like an open switch, okay, creating an open circuit, interrupting the current that's being detected on the other end, okay, by the electronic card. And this would be perceived, so this dip of current, of electrical current, would be immediately perceived as smoke on board, which is, by the way, very important because it is like an early warning system for incendiary events. In other words, the fire might have started in a compartment or in an area where you won't have necessarily a detector, a heat detector. Even like when you do have, at times, the heat detector is a little bit slow to act. Why? Because it takes time for an area in the aircraft to heat up, even if it's not a long time, but it would take some few minutes for that detector to heat up in order to signal an alarm in the cockpit, okay, of a fire. However, the smoke detector would detect the fire even before it actually develops and becomes mature. It would detect the smoking event, which is due to the overheating before, like while the fire is still under control, okay? While the fire is still smoldering before developing into destructive flames. This is the very importance of smoke detection systems. 15.2 Fire warning systems. Fire warning architecture. Okay, the fire detection systems interface with cockpit warning logic to provide clear and unmistakable alerts. Typical indications include master warning lights, fire warning lights like engine fire and APU fire would start flashing, and auto warnings, which is the fire bell, okay, fire horn. The warning logic and redundancy. Most systems require confirmation from multiple sensors in order to confirm that there is actually a fire on board. So most systems would require confirmation from multiple sensing devices in order to prevent false warnings. Because if one resistor breaks off, it can sound a wrong or a false fire alarm. That's why we need redundancy and backup so as to get the information from multiple sensors at the same time so as to confirm that there's indeed a fire on board. You have two loop logic, so fire warning is equal to loop A and loop B at the same time, okay? So the intersection between loop A and loop B. And fault detection logic, the fault is equal to loop A XOR loop B. That is an electronic logic over here. This actually means that both A and B should be detecting a fire, okay, in order for that to be considered as a fault, okay, as a fire event. So in other words, let me write it down. This is the electronic XOR. So this is A and B. If A sensor had detected a fire while B sensor had not detected fire, so that would be considered as no fault. Okay, there's no fire. If A did not detect a fire but B did, also it's considered as negative, okay, negative alarm. So there's no fault so far. But if A and B both had detected fire, then this would be considered as a correct fault alarm, okay? This would be like perceived as real fire detection. Okay, so it would be validated. So if A is yes, B is no, A no, B is yes, or both are zeros, by the way, also. If both did not detect a fire, then also that would be negative. Meanwhile, only if A and B both had detected fire, then this would be considered as a valid alarm, as a valid fire detection on board. Fire handles and crew interface. Fire handles allow the crew to shut off fuel supply in order to try to mitigate the fire and stop feeding it, isolate bleed air in order to suffocate or to starve the fire from oxygen. 3, disconnect electrical power, also to like disconnect to try to shut off any other contributing factors to the fire through electrical energy. And finally, arm fire extinguishers in order to extinguish the fire, especially within the engine. 15.3 Fire suppression agents and controls. Fire suppression principles. The fire suppression removes one or more elements of the fire triangle. This would be the heat, fuel, and oxygen. The three of them need to be taken into consideration, okay, and worked on in order to extinguish the fire. So the heat through cooling, the fuel to cut off what is feeding the fire, and starving the fire from oxygen in order to suffocate it, okay, to put it down. The heat release rate is given by Q equal mf delta Hc, okay? That is the heat release or transfer rate, equal to the mass of the fluid being, used for extinguishing the fire multiplied by delta Hc. Fire extinguishing agents, you have the halon agents traditionally used due to effectiveness and low toxicity. Okay, the suppression effectiveness condition is given by C of agent of the extinguishing agent should be greater than or equal to the minimum capacity. Okay, minimum extinguishing capacity. As for the formula, Q equal mf delta Hc, m is the mass of the extinguishing fluid again, and delta Hc is the differential of the heat of combustion, okay? So this would be the factor that would play a role in the extinguishing or the fire suppression. Alternative agents, environmentally friendly replacements include HFCs and inert gas blends. You have water and foam used in lavatories and portable extinguishers. Fire bottle discharge systems. Fire bottles are pressurized containers discharged electrically or mechanically. Discharge mass flow rate is given by M equal CD, capacity of discharge multiplied by A, square root of 2 rho delta P. Rho is the density, and delta P is the differential of pressure between the inside of the extinguisher, okay, like the inner gas of the bottle, and the pressure outside, on the outside, which is, in such case, the pressure of the cabin, in case you are extinguishing something within the cabin, okay? Or in general, it would be the pressure of the outside environment, all right? So M is equal to capacity of discharge times A, which I believe to be the area of the hose, times square root of 2 rho. Rho would be the density of the fluid, the suppression fluid, multiplied by delta P, or the differential of pressure between the inner container of the extinguisher and the external ambience or the external atmosphere. Now, time limited protection for cargo compartments. Okay, so that time limited protection would be given by CT is equal to C0, original capacity, multiplied by E, the exponential of minus KT. Now, in case you are wondering, C is the capacity of the extinguishing agent or the fire suppression agent within the bottle is given by the original capacity multiplied by the exponential of minus kT, with K being the decay rate of the agent, okay, because the agent concentration would decay with time. So after a specific interval of time, it would no longer be reliable and effective in fire extinguishing, and it would need to be replaced. Multiplied by T, which is the time. Okay, so this would be the formula correlating the running capacity or like the current capacity in factor of time and decay. 15.4 System testing and safety procedures. Byte or built-in test equipment. Okay, modern aircraft use byte to verify system integrity. Test condition is when the test passes, all the channels would be nominal. It would mean that all channels are nominal. Crew fire tests, cockpit fire test switches verify detection loops. Warning, because it's a loop circuit, okay, around a resistance that would detect the fire. And that resistance value would change based on the heat that is exposed to it. Warning lights and bells, these are the indicators and the sounding alarm, and fire handle illumination, which means that, for example, the engine fire would light up the fire handle, okay? It would be lit in order to verify that the alarm is actually working, the indicator is correctly functioning. Maintenance safety procedures. Okay, you have fire bottles, safety pinned before maintenance, electrical power isolated, leak and pressure checks performed, bottle pressure verification, so the pressure of the bottle should be greater than the minimum pressure. That's why it has like a pressure sensor, a pressure measuring device in bars, okay, that would be like a needle, an instrument for measuring the pressure of the extinguisher itself. Certification and reliability requirements. Fire protection systems must comply with FAR/TS 25 requirements. Okay, now the system reliability for redundant detection loops is given by R equal 1 minus R1 times 1 minus R2. That would be two resistors that are working together in order to verify the occurrence of fire. Final summary, fire detection and protection systems combine thermal, optical, and electrical sensing with robust warning logic and suppression mechanisms in order to ensure rapid response to fire hazards and maintain aircraft safety throughout all phases of flight.